building code, and they must also meet an energy standard. And so that began the quest to build a better home in Alaska. And because of that, we now are building homes that are using less than half of the energy per square foot that a home built prior to 1990 did. And a lot of that is the result of the energy programs that agencies developed over the years. And as we're building tighter homes, we have to be more conscientious about ventilation. Our motto was build tight, ventilate right. And as you build a tighter home and you're having less air exchange going through the house, you want to make sure that you have a good ventilation. When you tighten up a home, you can no longer use a combustion appliance like a wood stove or a water heater or a furnace or a boiler that is drawing air from inside the home. You have to supply air from outside the house into that appliance in order for it to burn properly and not spill pollutants into the home. Carbon monoxide being the biggest danger because that'll kill you. But also there's other, nitrous oxides and sulfur dioxide and all kinds of other stuff that you don't really want to be breathing. So, pardon me. But the difference in all of that is by building tight and ventilating right, and then making our combustion appliances safe, we can make sure that we're making the homes healthy, safe, durable, comfortable, and affordable. Then the other thing that we have to take into account is all the different building materials that we're getting coming in. We've got, we used to build with regular plywood. Now it's mostly an oriented strand board. We're using Tyvek. We're using all kinds of different materials in the houses, and how we incorporate those materials is really important. So a lot of changes. And as we go through it, this a house it's necessary for several things. First we want to make sure it's safe. That it's not going to collapse on our heads. It's not going to burn. Because somebody had a candle on the kitchen table. It's not going to cause problems and not do what we want it to. We want to make sure that it's keeping the rain and snow out. That's a little warmth and a little dry space for us to live in is the comfort part, right? Then, we got to do it in an affordable way. The economic means to make it, that we can afford to build it in the first place, but also it's got to be durable. So we don't want to, put something in and then have to go back and fix it the next year. We want to make sure that it's going to stick around for a few years. We don't want it to have adverse environmental impacts. We don't want to be breathing a lot of fumes and stuff from the materials off-gassing. We don't want to be causing problems with allergies and chemical sensitivities and all that sort of stuff. So we have to be conscientious about the materials that we use. And then finally, we want it to be, visually appealing. We want thermal comfort. We want it to be a relative uniform temperature throughout the house, maybe a little warmer in some areas, a little cooler in others, but we want to be able to control that. And all of that is important. And we do that through building codes and energy standards. And these are minimum standards. The building codes, a lot of people complain, oh, we don't want to have building codes in Alaska. We don't need building codes in Alaska. And I say, if you're building a recreational cabin out in the woods somewhere, fine, go for it. You're doing it out of pocket, no big deal. The problem comes when you apply that same mentality in town and you build a house that's not built particularly well and it's not built to code. And for whatever reason, your mother gets sick outside and you have to go move and you want to sell that house, somebody else inherits that problem, right? And so it's important. And also, if that house were to ever catch fire, the Kodiak Fire Department will not go into a house that is not certified to maintain a fire code. They'll let it burn, and they'll fight it from the outside, but they will not enter a house that is not on their list of homes that have met building codes, because it's a safety issue for the firefighters. And, you know, a deck like this one, you know, you have a bunch of people on the deck for a summer barbecue, you don't want that happening with all your friends on it, it's not fun. So building codes are important. Moisture is one of those things that will contribute to the degradation of a house very quickly. And it's, it can be caused by bulk water, rain, snow, and whatnot leaking into the home, but it can also be caused by moisture that's already in the home and then being diffused throughout the house. For example, we can have a wet foundation and concrete can actually, cause capillary action that'll raise the level of water up into the wood that's above the concrete foundation and then raise that into the insulation, degrading the quality of the insulation and causing moisture problems, which can cause structural problems and all that other thing. Moisture moves from wet to dry, and the dew point is where water vapor changes to liquid water. And then of course we have liquid water changing to ice when it gets cold enough, and hopefully that doesn't happen in our homes. So when we're looking at moisture, it moves from hot to cold and from wet to dry. And of course it exists as a solid, a liquid, and a vapor. And that capillary action that I meant, bulk water is, we definitely want to avoid this type of situation. But capillary action is where we can actually see water climbing up, like if you were to dip a paper towel into a cup of coffee, you can see that it's wet well beyond the level of the coffee in the cup. And that can happen in our house as well. But we also have air transported moisture, and this is the only way I can see to visualize this, but air transported moisture is where we have warm, moist air, again, rising and maybe leaking into the attic. And then it gets cold and it condenses and it drops all that moisture in the insulation in the attic and can cause problems. So we want to really pay attention to the relative humidity, and that's the amount of water vapor expressed as a percentage of saturation. So if we say it's raining outside, it's probably pretty close to 100% relative humidity outside. But the warm air can hold a lot more moisture than cold air can. And the general rule of thumb is a change in temperature of 20 degrees in either direction will either double or half the relative humidity. So for example, if we have our house at 70 degrees and 50% relative humidity, if we go to 90 degrees, the relative humidity, and we have the same amount of moisture in the house, the relative humidity is going to be cut in half, so it'll be about 25%. On the other hand, which is more likely in Alaska, if we go from 70 degrees and 50% relative humidity down to 50 degrees, now we've doubled the relative humidity and we've hit that saturation point where air changes from a vapor to a liquid. And if you get a liquid present in your insulation or on your wooden structure of the framing, the sill plates, the roof rafters, and all that sort of thing, and it's there long enough and it doesn't dry out, then you start getting things like mold and rot and structural problems from that. So we measure relative humidity with something like a relative humidity indicator. So there's the temperature on top, but the relative humidity on the bottom. And we generally say we like to keep the relative humidity in a house comfortable for people between 30 and 50%. It's both comfortable for people in that it's not too humid and we're not getting all kinds of viruses and bacteria and other things that are present when you get too humid, and it's not so dry that when you scuff your feet across the carpet and you go to pet the cat, you get a foot-long spark and it annoys the cat. So 30 to 50% is a really good comfortable level for both people and buildings. And we can generally avoid having condensation issues in our buildings if we keep it within that range. So what happens when air temperature changes? Our volume stays about the same, but the buoyancy can change. warm air is more buoyant, less dense than cold air. So warm air rising can have a lot of effect. The warmer the air is, the more moisture it can carry. And if we're carrying excess moisture and all of a sudden it hits a cold place, condensation happens, we get problems. So we got to keep water out of our buildings. This is an example of splash from the roof. You know, the water's running off the edge and it's hitting the ground. And if this is an 8-foot wall, we're seeing splash 5, 6, 7 feet up on the wall, just by splash. Well, this type of siding does really good job at preventing rain that's hitting it from an angle coming down, but it doesn't do very well at all when you're getting splash going up. It'll go right up behind that, drain down behind that siding. And again, if it stays wet long enough, you're gonna start getting rot and your wall will rot out. I lived in a house in Ketchikan that was built in 1950, and by 1990, they were on their 3rd wall replacement. 40 years, 3 walls were replaced because of wind-driven rain. So we have other things going on, like in the summertime, we have very cold groundwater here, and you'll get a lot of sweating pipes. If these copper pipes are in confined space in your wall, in a space, say, between your kitchen and bathroom, and they're constantly dripping and they never dry out, again, mold, rot, and all kinds of other things. So this was a house in Twin Hills. That's the house there. And this bedroom was on the back corner that's covered up under the little recording device there. But anyway, what happened was the prevailing wind was from this direction, and it would hit that, swirl around, and it actually moved this cellulose insulation to the point where it blew it, and it swirled around, created these little eddies and whirlpools, and the insulation was moved and exposed the bare vapor barrier underneath. And it corresponded exactly to that mold on the ceiling, because now that was the cold spot. These 3 spots here on the ceiling had no insulation on top of them, and there was enough moisture in the house that it was condensing and causing those mold spots. And the owner had no idea what was going on, but we walked in there, we took one look at it, went outside, crawled around, looked down in that area, saw the insulation had been moved around, got up there, raked it out. We ended up getting just some fiberglass insulation put on top of that corner, cleaned the mold spots off, and it never returned. So it was a fairly simple fix, but unless you knew what you were looking for, you'd never find it. The owner had cleaned that numerous times and had finally given up on it. So there's a picture of the house. It was this back bedroom over on this side. The wind just swirled around in that little gable end.
So through the gable end vent, the wind was coming through?
No, it wasn't a vent necessarily. It was just those E vents. You know, the gable or the E vents were open enough, and it just had the right combination of wind. Twin Hills is a windy area. There's constant wind in that area. So it was enough that it was just swirling around, and it moved the insulation just enough that it caused that problem. Another problem that we see frequently from bulk water, this is just splash coming down, hitting the area in front, and these logs are starting to rot out. So a bigger overhang or gutters to help control that water coming off the roof is important. And the problem, of course, when wood gets wet, we end up with mildew and rot. So there's 3 ways to deal with water problems in wood. We keep water away from wood, we don't let wood get wet, and we keep wood dry. But when wood does get wet, we have to deal with it. So one of the ways we try to prevent it is using pookie. And that's your common stuff. If you go out to the retrofit table, we've got all kinds of pookie that you can practice putting around different holes in your ceiling and whatnot. You can caulk with confidence out there. And but we should never really rely on pookie, tape, and goo for sealing our buildings. We want to shed the water as it's coming onto the building, not relying on sealants to keep it from happening. So, I mean, this is a maritime community. We can all envision, rain gear, right? And if we look at this one, it's a little hard, but this guy has his jacket tucked into his bibs and his bibs tucked into his boot, right? So what happens when the rain hits this guy? The water runs right into his boots, right? That's exactly what we don't want to do in our buildings. We want to overlap from the bottom up, so we'd have the legs of his bibs out over his boots, and we'd have his jacket out over his bibs. And that way you're shedding the water, and you don't even have to worry about, if you're trying to put tape on this to keep the water out, how well is that gonna work? I mean, just look right here, below the tape, it's just you can't do it. It's just not possible. So we flash from the bottom up, we start with the bottom strip, and then we do the side strips, and then we do the top strip, whenever we're doing flashing. We start our siding, lap siding from the bottom. We start our shingles on the roof from the bottom and work our way up to the top. Shed the water. When we're cooking and showering, we have to deal with moisture. We deal with that through ventilation. And we also want to make sure that we put a good vapor barrier inside on the warm side of the insulation. So if the yellow line is indicative of the insulation, then the dark blue line in here is the vapor barrier. And we always want to put the vapor barrier on the warm side of the insulation so that we can keep that water in a vapor state inside the building and not have it as liquid water in these interstitial cavities, in the attic or in the walls. Heat is, as we mentioned, comes in three forms. It's radiation, conduction, and convection. If we are thinking about radiation, if you have a wood stove, even across the room, and you're sitting over here, you can feel that heat if you're in a direct line from it. The radiation heat from the sun is what you feel when the sun is on your face outside. And so it's direct line of sight, and it's transferring heat from the source to the object in the house. And it's an effective form of heat transfer, but it can be blocked. If you have a person or another object between you and the heat source, you're not going to feel it. Conduction is if you put your hand on the table and hold it there for 15 or 20 seconds, my hand is warmer than the tabletop. And it doesn't have to be long, and I can move away, and then I can move back, and I can feel it's colder over here than it is where I had my hand. And I've conducted heat from my hand to the tabletop. It moves from hot to cold, and it's just another form of heat transfer. And then we have convection, which is the warm air rising and the cold air falling. And that can happen in our homes all the time, and that can have tremendous effect on comfort issues. And then cold is just marked by a lack of warmth. There really isn't a term in physics for cold, except for the absence of heat. And oftentimes, we refer to cold as just something that's uncomfortable for our human condition. So heat flow is whenever we have, two objects that we're trying to warm one, it's going to move from hot to cold. We can do that, with radiant floor heating, for example. So you're pumping a warm fluid through a floor system, and that heat's going to transfer into the house. Convection, we can have problems both in the building where you have the warm air up near the ceiling. You've probably all been in houses, particularly houses that have maybe a loft and a little cabin or something where it's very warm up in the loft and it's quite cold down on the floor, right? That's because of convection. But we can also have convective loops inside a wall where there's insulation. And if there's moisture or penetrations in our vapor barrier, we can have warm, moist air penetrating through, say, an electrical outlet or a light switch, and that goes into the wall. And if there's a convective loop, oftentimes our walls are only 6 inches thick, and it's 70 degrees inside, and if it's really cold outside, say 0 outside, we can get quite a convective loop going in a 70-degree temperature difference over 6 inches. So we can have that warm air rising and the cold air falling, and that moisture is going to go up and it's going to come down and it's going to start condensing out here on the inside of the wall, and that's where we can run into problems. And then we have air. Air is always around us. It's good. We like to breathe. But it's something, that you can't train it to follow arrows on a diagram. It moves like rivers, cheap labor, and a lot of teenagers takes the path of least resistance, right? So we have air movement, and again, air movement can warm air can carry a lot of moisture, and we can see where we have a situation, say that we're looking at warm air will actually diffuse moisture through a material, say like this door behind us, behind you guys over here. You can get a little bit of moisture that will diffuse through that door over time if you have a pressure differential and a temperature differential. But if you have a little bit of a hole, and you have a place for that air to go, you can have a dramatic increase in the amount of moisture. So the equivalent here is like, if it's just looking at, a very tight ceiling, for example, and we're just looking at vapor diffusion, we have almost no air leakage. And, in a year, we might transfer maybe a gallon of water through a ceiling that's airtight. But by the same token, if we have just a little hole, we can carry hundreds of gallons sometimes. And you think about, if you've ever had a kid pull a gallon of milk out of the refrigerator and drop the bottle, and milk goes all over the floor, a gallon's going to make a pretty big mess, right? Anybody ever have a washing machine leak? Where the hose came off the washing machine? That's huge. That's like 20 to 25 gallons. So we think about a couple 100 gallons going into our attic and into our walls in a year. That's a lot of water. So what do we do about that? We want to slow that air movement down. And we have, as I talked about, the stack effect of warm air rising. We have wind on the building can make a lot of difference, because if the wind's coming, say, from this direction, let's do the diagram from this way. So you have pressure on this side, and you have, this is the lee side, and it's actually going to create negative pressure on this side. So you can have air inside the building moving this way. And then we have mechanical systems, furnaces and ventilation systems that are moving air around inside the building as well. If the building is static and there's nobody inside, and a typical older home built, say, back in the pre-1990 era, there'd be a lot of leakage up in the ceiling plane here, and a lot of leakage down here, and a lot of cold air is coming in down here, and warm air is leaving here. At some point between here and here, we'll have what's called the neutral pressure plane. And above that, air is going to be leaving the building. Below that, air is going to be coming into the building. And so one of the things that we want to do is we want to stop that from happening. And the easiest way to stop that is not coming down here and sealing all these leaks down at the bottom. It's getting up here and sealing the warm air from leaving the building at the top. And if we can do that, that's actually a lot safer. And I'll talk about that in a little bit. And here's how air moving over a building can create different pressures. Inside a building, we also have lots of different ways for air to move that you may not see. So this is a chimney chase, and it's sheetrocked on both sides. So from the inside of the living space, you're just going to see sheetrock and maybe a little rectangle. But inside, there's this huge hole that's moving from the bottom of the building all the way through to the attic. And if you've got something like that, there's a chance for a lot of moisture to be moving through there and a lot of warm air that you've already paid to heat and moving it out. And if you've got that much moisture or warm air moving out of the building, you've got to replace it with cold air coming into the building at the bottom, and that's going to make it uncomfortable. And you can also have durability issues as well. So you really want to stop it from leaving at the top. It's going to stop it from coming in at the bottom. You're going to hold that heat in the building that you've already paid to heat, and it's going to make the building a lot more comfortable for you. So find and fix the leaks, start at the top first, attic hatch, recessed lights. And if you go out to the retrofit table, there's demonstrations out there where you can look at all the different holes and penetrations that we have in the ceiling, vent pipes and chimney stacks and light switches and light, wires and all kinds of different things to look at. These plumbing stacks can do this, but this is one that I took a picture in Sellewick. And I popped my head through the attic hatch and looked up here because the owner said, I've got this problem. The light fixture had a globe on it, a round glass globe, and it was about 2/3 full of water. And all the dead flies are in there floating around. And they said, where's all this water coming from? We don't have leaks in the roof. I popped my head through the attic hatch, and right here, there'd been a garbage bag full of clothes that somebody had gone up there and just, set a bag of clothes that they weren't using on top of the wire that was going to that light switch. Warm, moist air moving up, condensed on the bottom of that plastic bag of clothes, and dripped down the wire right into the light fixture and filled the light fixture with water. This is a bath fan that was in Palmer that our weatherization program had put in, and the owner complained that there was some water dripping back into the building. And we went and looked, and we could see the water stain all around the bath fan. And when we looked, the housing of the fan had cracked and come apart, whether accidentally or through negligence of the contractor, we don't know. But the upshot was all this warm, moist air from the showers that everybody was taking, they were trying to exhaust it out of the building, but it was coming out through this crack, air taking the path of least resistance, and it was just soaking into the insulation and starting to drip back into the bathroom. No fun at all. In Anchorage, this house had just air leaks, and you can see all the frost built up on the inside of the boards on the attic, and the warm air is coming up here, and that's where a source of all the moisture is coming from. This is not an external picture. This is from inside an attic. And this is a gable end vent from inside the attic, frozen 3/4 of the way. This only here is the only part that's ice-free. There's a lot of moisture coming up into that attic. What happens on a day like today, when you had that happening, and all of a sudden now the temperature is 45 degrees outside? That all melts, right? Now it soaks into the insulation. We have the typical January thaw. Well, guess what? Next week it gets cold, right? It's forecast to go to 8 degrees on Thursday. And all of a sudden, you're cold in your house and you don't know why. It was fine earlier in January when it was 8 degrees. Now in February when it's 8 degrees, I'm cold. What happened? Well, my insulation got really wet and it doesn't work. And all that heat you're paying for is just leaving right out the top of your building. Heat loss to the attic can also cause roof ice. We haven't had enough snow this winter to have this be a real issue, but there's some winters where we get a couple of feet of snow on top of a roof and we get a lot of roof ice. And what happens there is you got warm air that's leaking up. The snow is actually acting as an insulation blanket. It's running down once it gets out to the eaves out here. It's cold out here and it freezes, and over time it begins to build up, and you get water that's actually backing up back here. And if you don't have the ice and water shield that is called for by the building code, that water is going to go under your shingles and drip into your house and soak your insulation, and your insulation's not going to work and your roof can run off. I hate it. So, you know, some people say, well, I'll just put heating cables on there, which makes for very, nice icicles, but, it doesn't really solve the problem. What we wanna do is, you know, get up there and stop that warm air from leaking up into the attic in the first place. Because when those ice dams break here, if this is a big chunk of ice, you can see there's a gutter right there. If that ice breaks off, it'll take that gutter with it. Now you just have a $400 or $600 bill to get that gutter replaced or more. And so, you know, that's one of the durability issues. So if we make the house energy efficient, we make it more durable so that we don't have to pay for stupid repairs like that. Go ahead, Frank.
Could you tell with an infrared picture really fast whether a building needed that in the attic? Like from the outside, if you took an infrared picture?
No, you don't even need an infrared. What you do need is certain snow conditions. Especially, it works really well if you have like, say, 4 inches of snow or less on the roof. It works great if you have just a little dusting, maybe a ½ inch or an inch or so. Because you can just see the spots on the roof where the snow is melting, and you don't need an infrared. You can just see, snow melts heat loss, and you can tell the spots where it's leaking. And oftentimes you'll see it around the attic hatch. You'll see it around the fan vents for the bathrooms, the dryer vents, the plumbing stacks, you know, those types of things. And you can just see it.
I've seen it in Homer where all the birds just pick one roof. So I figure they were going for warm too.
That may be, it may be. Take a look at the snow melt the next time, you know, when, Monday or Tuesday, when it starts to snow again, go out there and look at that building just as as the roof's starting to get covered, and see where the melt patterns are. As we do all this, we tighten the building up, we can end up with indoor air quality issues. I've mentioned some of them: carbon monoxide, nitrous, sulfur dioxide, particulates, you know, all that sort of stuff. Cleaning products have gotten better over the years, but there's still stuff that we bring into our homes that, as it off gases, it can actually cause problems. And if we don't get rid of those pollutants in our homes, it can really cause, you know, people with chemical sensitivities in particular, or people with allergies can have some real issues. Come on in and take a seat if you want. Welcome. It's my lovely wife. Chris.
What about natural gas in that?
What about natural
You
gas?
have natural gas appliances and things like that.
So if you've got say a natural gas cook stove, when you're running, it's probably not a big deal if your burners are reasonably clean, you know, if they're not completely caked and you haven't cleaned the stovetop in, you know, 7 months. If your burners are reasonably clean, the stovetop is probably not too much of an issue. But I would definitely run the exhaust fan anytime you're in the oven, because this, particularly on startup, cold oven, natural gas fired oven, will produce a fair amount of carbon monoxide. And if you're running that exhaust fan, it's coming out, it's going into the exhaust hood, and it's getting exhausted outside, that's not a problem. If you let it build up in a house, particularly a tight house, then you can have potentially enough carbon monoxide it probably wouldn't, you know, put you into an unconscious state, but you could end up with headaches. And the carbon monoxide actually mimics cold. So you can get stuffy nose, you get a headache, maybe your scratchy throat or something, and you'll think, oh gee, I'm coming down with something. But you go outside and you feel better, and you come back into your house and you feel worse, you got a problem in your house. You know, I haven't heard of a natural gas oven or stove really causing problems, except if people are trying to use it to heat the house during a power outage. And don't laugh, it's a true thing. And people have died, you know, when they tried to heat their homes using their ovens during power outage. It's, you know, it generally, once the stove warms up and is at temperature, it's gonna burn more cleanly and not produce very much carbon monoxide. But if you're leaving it on for hours and hours and hours, and there's some speculation, I don't know how true it might be, but there is some speculation that it's not the tryptophan on Thanksgiving turkey that puts people to sleep after the big meal. It's carbon monoxide because the oven's been on all day. I don't know, I've never tested that theory, but it's a thought. So this is a house in Fairbanks that I went into, and it was kind of tragic because it's kind of the epitome of a lot of the different things that I've been talking about. I mean, here you can actually see the studs in the wall and the nails and the screws that are holding the sheetrock on. Again, what's happening here, high moisture content, low ventilation, and you're seeing condensation happening on every cold surface here. And it's creating a space, dust will start to stick there. And dust, of course, has organic material. Mold needs three things. It needs food, it needs moisture, and it needs oxygen. Oxygen is ubiquitous, it's everywhere all the time. The food is the dust and the organic material that might be in the dust. And then the moisture is just the water vapor condensing on the cold surface. So we can see that on the wall studs. We can also see down here, this is concrete block with no insulation. And so that's worse down there. And you can even see the green in the algae. But up here, this is poorly installed insulation here. And we have situations where somebody just wasn't too careful about how they put the insulation into the building in the first place, and that causes these voids, which are colder than other spots. And but you can see also the toys. This is a child's room, and you know, having to grow up in a room like this would not be very much fun. So build tight, ventilate right. We don't want to put a plastic bag around our house and keep all of that moisture and pollutant into the house. We want to ventilate all the moisture and pollutants out of the house. The other thing we also want to be a little bit conscientious of is car exhaust in our garages. It's better now because most vehicles have pretty good emissions control on them. And but when I first started doing this in the early 90s, a lot of people have 10, 15-year-old cars frequently. And so if you were parking a 15-year-old 1995 car, that was 1980, you know, age car, they produced a lot of carbon monoxide on startup. And so a car like this, this was actually a test that was done, and they opened the garage door and they started the car and they let it idle. And you think about how you go in the morning when you're getting ready to go to work, and you go out and you get in your car, and you turn the car on, and you know, Julia is a lot shorter than I am. I always have to adjust the seat, and then I have to adjust the mirrors, and she likes a different radio station than I do, and so then I gotta put my seatbelt on. And so the car might have been running for 30, 45 seconds. Before I start moving out the door. Even with the garage door open, in this case, when they did this test, they started the car, and in 45 seconds, 200 parts per million carbon monoxide at the front door of the garage over here. And 200 parts per million is enough to knock you out and put you down. It's not probably enough to kill you unless you stay in it long enough, but it is enough to knock you out and put you down. And so really be conscientious, and if you can, open the door, back the car out of the garage, then adjust the radio station, put your seatbelt on, and all that sort of stuff. Newer cars, better emissions, not as much of a problem, but if you've got older cars, definitely something to think about. So our house is a system. We want to make sure that we have good insulation for energy efficiency. We have a good vapor barrier for moisture control. We have ventilation to get rid of the moisture and pollutants. And you know, the one other thing that we might want to talk about is combustion appliance and combustion safety. So if we're a typical old style wood stove, or furnace or water heater, drew the air from inside the house into the firebox. It burned, you know, that provided the air for combustion. It burned the stack effect, the warm air rising, forced the air up out of the chimney, and the pollutants left the building. But what happens if you turn all these fans on? You've got a fairly tight house, and you've still got wood stove that's drawing air from inside the house. Now you can reverse the flow, and all of a sudden you're filling your house with smoke. Well, if you got a wood stove, you're gonna do something about that pretty quick, because the smoke's gonna annoy you. But what if it's a water heater and you can't smell that carbon monoxide? What if it's a furnace and you don't know that that furnace is backdrafting and drawing that air into the house? So we wanna make sure that when we do put our appliances in, these are called naturally aspirating combustion appliances. That means it's drawing air from within the space where they're located. If we can either provide fresh air to come into the space or provide fresh air directly to the appliance, that's a whole lot better off. And then making sure that they're vented properly. Again, if you have a naturally aspirating appliance, it's the warm air rising that's going to get rid of those exhaust gases. That one there is pointing downhill. It's not going to exhaust very well. I took that picture in Anchorage. This picture in Fairbanks, I don't even know what they were thinking. There's 13 elbows that they put there. These things, you can straighten them out, make straight pipe out of them. For every 90-degree bend, it's the equivalent of adding 10 feet to pipe. So this is like 130-foot equivalent to pipe. And who knows? I mean, these are just some of the things that I personally have seen as I've been in houses around Alaska. This is a good example of what backdrafting looks like. You see a lot of soot right at the bottom of the draft hood. And there's a lot of material, dark material that's right there. That means that that water heater has been backdrafting and spilling combustion gases into the living space. So we want to stop that. But once we do this all, go ahead.
So, the pipe length, contributes to like resistance to flow.
Yep.
Yeah,
Yep.
does not ever help, like taller.
The
better.
shorter the pipe, the better off you are.
Okay,
The only exception to that is when you're above the roof and you want to make sure that the chimney is at least 2 feet above the nearest point, within 10-foot radius.
code requirement,
Yeah.
yeah,
Well, not only that, but just for practical, making the draft work.
okay. And that has to do with turbulence?
No, it actually, if you're looking at say this here, if this was cut off low to the roof line
Yeah,
here.
yeah.
There's not enough draft to get outside of the influence of the roof. You wanna have this piece of the pipe at the top here, at least 2 feet above this point, 10 feet away.
Yeah,
And that's kind of the minimum rule of thumb. We had a wood stove put in, what, 3 years ago? Something like that. And we had to add another stick of pipe to get it above that point because it wasn't drafting properly.
that's the exception.
Yeah.
That's the exception.
Yeah, that's the one place where you want a longer pipe. But otherwise, inside the building, you want to do as much vertical as you can, as few 90-degree bends as you can, and as short as you can.
The 90s are all drag all the time.
Well, they're equivalent to like 10 feet
Yeah.
of pipe. Yeah, so, yeah, if you can avoid them. But once we do all this, you know, our homes are gonna be safe and healthy without carbon monoxide, without mold and uncomfortable stuff. They're gonna be comfortable. We're gonna have more even heat sources around throughout the building. They're gonna be more durable. They're not gonna be rotting. They're gonna be affordable because we've contained the energy that we've already paid for, and they're gonna be reducing carbon emissions and pollution to the outside of the building. And when we do that, it will look something like the insulation, the vapor barrier, the ventilation, we're exhausting the pollutants, we're getting some fresh air coming in, we're getting the moisture out, and then we put a carbon monoxide and smoke detector in, just in case. Hopefully we never need to use it. And carbon monoxide detectors are generally good 5 to 10 years, so I'm kind of embarrassed to say that Julie had a situation a couple of months ago where we had a smoke alarm go off, and we had a combination of smoke and carbon monoxide detectors. When I pulled it down, it was 15 years old. And so I had to replace all 6 of them. It was probably a good thing that it did happen, because I had not been paying attention to it. And 5 years slipped into 15 years pretty easily. So, thanks for coming, and I'm glad to take any questions. Go ahead, Mike.
Does the average construction company in Homer understand it? Two related questions. Does the average construction company in Homer understand the science? And secondly, how does the average homeowner or to be a homeowner know whether that construction company understands the science?
One of the ways to answer your second question first is that contractors in Alaska are required to have a residential endorsement if they're building homes. And if they have that residential endorsement, they've at least been exposed to these types of classics. They have to take 20 hours every 2 years.
2 years?
At least 20 hours classroom time every 2 years to understand building codes and energy efficiency and, building safety and all the stuff that I've been talking about. So if they have a residential endorsement, which you can ask them, if you're gonna hire someone, do you have a residential endorsement? And they say yes, you can trust that they've at least been exposed to it. What you can't really tell is whether they apply it. But there are some things that you can look for as they're building the home. Are they building areas around the chimneys that are, 2 or 3 times the size of the chimney, like that picture I showed you? And if they are, do they have some way of sealing that at the top and putting something around, like sheet metal around the chimney itself, and then caulking and sealing that at the top of the building? You can look for those types of things, and you can tell them in your contract, you want, the other way to do it is you can say, I want a 5-star or 5-star plus or 6-star energy rating. And, the higher you go on the star level, the more you're gonna pay. But generally, I would say 5-star is the minimum right now. 6-star is the deluxe version. And if you ask for a 6-star, you might pay, I don't know, $8,000 to $12,000 more for a 6-star home over a 5-star home. But you could rest assured that most of these issues are gonna be dealt with in a 6-star home.
Okay.
Only a few of them might be dealt with in a 5-star.
Could you answer my first question first now?
How do you know that contractors?
No, the first question was, do construction companies at Homer?
Oh, yeah, there are definitely construction companies that do know this, and there have been some very good contractors in Homer. The ones I know are retiring now. But I know there's probably up and coming ones that are probably doing a pretty good job. I just don't have any personal experience. I'm not gonna say yay or nay as to whether they have it or not. The ones that I do know are for the most part retired now, so I can't say.
Thank you.
Right.
Have you done any comparisons between countries, or is it always United States, like how Germany builds and France builds?
I work quite frequently with Canadians. I don't know if that's helpful or not, but, they, you know, they live all north of the 48th parallel and, with a few exceptions, most of their winters are at least as cold as most places in the United States. And so a lot of this building science that I'm presenting today came to Alaska from Canadians. We've also had influence from the Swedes and the Norwegians, and Finns. And I've read a lot of studies that do make comparisons worldwide. You know, there's very, very good homes built in the US that are comparable to anything that's built anywhere else in the world. It's just a matter of cost.
I remember being in Germany trying to put a nail in the wall and I thought it would be easy, and it wasn't, because they built things for like 200 years, not for
Yeah.
20 years. Like,
Well, you know, it also depends on when a house was built in Germany. You know, if it's a 700-year-old house, it's gonna be a little different than a house that was built 4 years ago. Lucas is from Belgium, he's probably got 700-year-old buildings where he lives. And, you know, they're gonna be very different, even when they've been retrofitted, you know, and they've probably been retrofitted a dozen or more times. And so you can have compounding problems from that, but you also have 700 years of experience in those areas that tell you how to build in that particular climate. So, you know, there's pros and cons. You know, you wonder why the Swedes all build really steep roof houses. Well, they get a lot of snow there. Go figure.
So there will be a door prize drawing at 3 o'clock. If you have not filled out the little slip, you'll need to do so in order to be eligible for the door prize. Is anybody not filled out the little slip? Raise your hand if you haven't filled it out.
I got one for you.
You've got one. Oh, okay.
Chris,
Do I come with radon gas in this area?
there is some on the Kenai Peninsula. There have not been any definitive studies that show specific places on the Kenai. There have been places where radon's been detected sporadically, in different places, but I don't know of any maps. There's been more study in the Matsu Valley and in Fairbanks, and so we have better maps of those areas than we do on the Kenai. There has not been a lot of effort to collect data on the Kenai Peninsula, so we don't have very good understanding of where radon might be. But it's an easy enough thing to test for. And I could do a whole nother class on radon mitigation, but
That's next year.
suffice to say that you can install basic radon mitigation ready stuff for under $300. And why not? If you're building a $300,000 house, spending $300 on radon mitigation is kind of no brainer to me.
What is it in general? What is the mitigation?
You can just take a perforated PVC pipe like drain tile, put it underneath your vapor barrier across the center, and do a really good job of sealing your ground vapor barrier to the walls. And any radon that's coming up through the ground is gonna migrate to that pipe. And if it turns out that you do have radon, when you test for it after your house is closed in and built, it's easy enough to put a fan on that pipe and exhaust it out.
Because it's a gas.
It's a gas.
The Homer Library has a radon detector you can borrow. You can do it.
And the University of Alaska in
Yes.
Fairbanks has radon testers that you just set in your house. And you leave them there for like a week, and then you send them in to a lab and they get tested.
Thank you, Scott.
Yep.
Okay.
Thank you.
Stimulating presentation. Ladies and gentlemen, that concludes our 3 presentations today. We hope you've enjoyed them and got lots of information from. Don't forget, Scott is still available in the exhibit area for the next hour as all the other exhibitors. enjoy your 1 hour here. Thank you for coming. Hopefully you can see you sometime in the future. And don't forget also that the presentation will be available online.
I read your.